Listen to the engine and listen to it roar. Something, Wabash Cannonball. I don't know. We're looking at Unit 6, a motion problem, or a force problem, A.5, and it's one of the asterisk problems, a little bit harder. This one's going to use a bunch of things in it. In this problem, we actually have connected objects, and we're going to have 3 connected objects, and we're going to include friction into this problem. So let's see what it is and what's going down here. In the problem, we have a child, and they're pulling on a toy locomotive of mass 0.979 kilograms with some force 3.25 newtons to the right. The locomotive is connected to 2 train cars by cables. Friction in the axles of the trains result in an effective coefficient of kinetic friction between the floor and the train, which is 0.11. One car's got a mass of 0.952 kilograms, and the other has a mass of 0.419. What's the acceleration of the train, and what is the tension in the cable between the locomotive and the car connected to the locomotive? I feel like I just read War and Peace, but let's work through this, okay? A kid is pulling on a toy locomotive, so let's just draw a poor, locomotive, okay? This is my train. Choo choo. So this train has a mass of 0.979 kilos, and the child is pulling it with a force of 3.25 newtons. The locomotive is connected to another train car. This one has a mass of 0.952, and then that train car is connected to another, which has a mass of 0.419. I'm going to call these masses 1, 2, and 3 respectively. Okay? Now we also know that there's some friction acting on these train cars. So when we take a look at the friction, maybe I'll draw some friction underneath here just so I get an idea and remember that friction does indeed exist. So that's kind of our picture there. So let's see, what can we do with this picture? What's going on? Well, I'm looking for the acceleration of the train. So that's the acceleration of the whole thing. Now, if we think about this, in each of our cables connecting the cars, there is a tension, and it's an equal and opposite tension. So let's call this T1 and T1, and then we'll call these T2 and T2, because these tensions are the same, they're just opposite directions. And we know that each of the cars, as we drew in the friction, has some frictional component to it. So we'll call this friction 1 for the first car. We'll call this friction 2 for the second car, and we'll call this friction 3 for the third car, okay? And if we wanted to draw this out as a free body diagram for each of these, here's our first car. We'd have 3.25 as a force going this way, and then to the left, we'd have T1, and we'd also have here some F1. For our middle, we'd have T1 and T2 and F2. And for our last one, we just have T2 and F3. Let's pick a direction to be positive. Let's pick right to be positive and left to be negative. If I want to find the acceleration, I can actually think of this entire train, the whole thing, as one system. And the beauty of that is a lot of these tensions that we don't know, the T2s, the T1s, are going to go away. If I sum the forces for this system to equal the mass total times the acceleration of the system, the acceleration of the train, what we'll actually get here is, starting from the right and working our way left, so starting over here in the 3.25 and ending in F3, is we'll have 3.25, which was positive, minus T1 minus F1, plus, so now we're onto the second car, plus T1 minus T2 minus F2, plus, now we're onto the third car, T2 minus F3. This will equal the mass of all of the train parts, mass 1, 2, and 3, multiplied by the acceleration. Oh, that's the biggest thing we've written out all year, but it's going to get a lot smaller. Negative T1 and positive T1, boom, boom, they're out of here. Negative T2 and positive T2, boom, boom, they're out of here. So all we have now is 3.25 minus F1 minus F2 minus F3 equals, well, the sum of the masses together, which, what would that be? If we go back up, let's just add them together. That's 0.979 plus 0.952 plus 0.419, that's 2.35. So this total mass here is 2.35 times the acceleration, okay? But what are we going to do about these frictions? Well, we know that friction is fun. It's mu times n. And we know that this normal force, because we're on a horizontal surface, the normal force will equal the weight here. Okay, when we're on a flat surface, whatever the weight is, the normal force will equal that weight, which is just m times g. Now, since this same coefficient of friction is applying to every single object, we can actually say that F1, F2, and F3, well, they're all going to be the coefficient of friction times mg, right? And they all have the same gravity and the same coefficient, so when we're adding them up, we could actually just add up all the masses. F1, F2, F3 together would be like mu g times m1 plus m2 plus m3, because this is F1 and then F2 and then F3. So we can actually write this as 3.25 minus, and then this will be 0.11, that's mu, that's our coefficient of friction, times 9.8, that's gravity. And then what's m1 plus m2 plus m3? Well, that's 2.35. And that will equal the 2.35 times A. If I multiply all the friction amounts together, so 0.11 times 9.8 times 2.35, I'm going to get the following. 3.25 from the initial force minus 2.53 equals 2.35 times the acceleration. If I subtract the 3.25 minus 2.53, I'm going to get 0.72. So 0.72 equals, and then I divide each side by 2.35, so 0.72 divided by 2.35 gives us the acceleration, which is 0.306 meters per second squared. That is our acceleration. Whew. So that was a little bit bigger than normal. A little bit bigger than normal in order to find that acceleration. Definitely a longer problem where we combined a lot of things together. But we're still not done. Our second part of the problem was, what's the tension in the cable between the locomotive and the car connected to it? So what is T1 equal to? Well, we could solve this by either using this free body diagram or this one. I don't know what T2 is though. So if I actually wanted to solve that, I'd have to go and use the last one first and then sub T2 in here. And that's more work than I want. I could if I wanted to though. But let's stick to this green one up here. Let's use this because I know enough numbers in there that I could easily solve this out. If I set up the F equals ma for this, I'm going to have 3.25 minus T1 minus the friction one, and that's going to equal the mass of just the first car, m1, times the acceleration of the system. We just solved for that acceleration of the system, if you recall. It was 0.306. So we can start solving this equation out. We're going to have 3.25 minus T1 minus, got to be careful here with friction. Friction is going to be mu times n, so 0.11 times mg, so 0.979 times 9.8, because that's m and that's g. and that will equal the mass of the first car, 0.979, times the acceleration we found, which is 0.306. Whew, a lot of numbers, but we can solve this. Let's multiply all of this together to get a number, and we'll multiply these together to get a number as we're just solving this through. So for my friction, 0.11 times 0.979 times 9.8 gives me 1.05. And for my MA, 0.979 times 0.306 gives me 0.3, pretty much on the dot. These are all in newtons. There's a minus T1 here, and then the 3.25. All my numbers that I have, number, these are all like terms, so I'm just going to combine them together. And then I just need to solve for T1. So to do that, I'm actually going to bring T1 over to the right. I'm just going to add T1 to each side. And I'm actually going to take my 0.3 and I'm going to subtract 0.3 from each side so that my 0.3 goes away and it comes over here with my numbers, and my T1 goes to the other side. So what I'll see now is 3.25 minus 1.05 minus 0.3. So 3.25 minus 1.05 minus 0.3 equals T1, and we find that T1 equals 1.9 newtons. Oh, what a problem. What a problem. But we technically knew everything that was going on there. We did it the exact same way we've always done it. We drew a picture. We set up free body diagrams, just with a little bit more forces than normal. If we were looking for an acceleration in a system, we set up the entire system equation. We were able to cross out a lot of the unknown action-reaction forces. For our friction here, we could have just written that as mu n, mu n, mu n, but we realized that we could write it out mu g times each of the masses together, which gave us a little bit faster way of solving that, to find that acceleration. And then we used that acceleration in a second equation, from our locomotive, in order to solve for T1. Okay? And that was it. That was the whole problem. So probably one of the bigger ones we've done of the year. That's why it's got an asterisk next to it. And if you can solve this problem, you should feel really good about pretty much anything that's going to come your way in this intro physics course. We could always make things arbitrarily more difficult and have a train with 100,000 cars to it, but there's no reason to do that. All the problems work out to be the same, and if you can do this one, you're pretty much good at anything that I could toss at you. Okay? So for now, this is finished. I hope you enjoyed this harder problem. Until next time, adios, and take it easy.